Hello, ladies and gentlemen. My name is Mrityunjay. I am from Quantum Research and Development Lab of University of Calcutta. And today I want to discuss on the topic that the impact of quantum technologies on the next era of computing world. First of all, to start with the topic, we want to know, we have to know what quantum computer is. The quantum computer is basically a machine which relies on quantum mechanical phenomena, which do calculations on quantum mechanical phenomena, quantum superposition, so quantum and quantum entanglement. And the quantum mechanical phenomena, the computation is much more faster. It computes that faster as in a lightning speed. Like I have given in the presentation that with a high performance computer of gigahertz capacity to break 2048 RSA key. RSA stands for Rivest Adelman and Rivest Shamir and Adelman. Shamir is one of the scientists of them. To break that particular key, it will take 317 trillion years for a gigahertz capacity high performance supercomputer. But for a quantum computer, if still we don't have, but for a quantum computer, it will take only 10 seconds if we can have in the near future. The next thing, but the problem is how a quantum computer is doing these computation so fast. The first thing is qubit. Qubit is basically the basic unit to represent a data for a quantum device. It can use 0, 1, as well as the combination of 0 and 1 simultaneously, so that the enormous volume of data can be taken together for a parallel computation. Now, to go a little bit technical, say a single qubit that is quantum bit can store data 0 and 1 simultaneously. Let us consider it is 50% 0 and 50% 1. So 1 qubit, I can have either 0 or 1. If I consider 2 qubits, then for the first qubit, I have 0 and 1 as well as 1. And for the second qubit, I have again for a superposed qubit, which can have 50% 0 and 50%. So if we combine these 2 qubits together, then we can have either 0, 0 or 0, 1 or 1, 0 or 1, 1. But in classical computer, whenever you have 2 bits, then you can have only either 0, 0, specifically either 0, 0, or 0, 1, or 1, 0, or 1, 1. That is, among these 4 possibilities, you can have only one options to store it. But in qubit, since I can put 50% 0 and 50% 1, so I can have all these 4 combinations together. That is 0, 0 simultaneously, 0, 1 simultaneously, 1, 0 and simultaneously 1, 1. Obviously, the probabilistic measurement of these values should not be always 100%. It should be 25% if it is fully superposed. That means each and every qubit is 50% 0 and 50% 1 with 50% 0 and 50% 1 probability. Then we can have these 4 combinations. Now consider 3. Then we can have 8 combinations from 0, 0, 0 to 1, 1, 1 with 1 by 8 probability. All the value will be there in only 3 qubits. Now consider 30 qubits. then you can have 2 to the power 30 values together over there with a very small probability, same and small probability over there in those 30 qubits. I can tell you one thing that within 60 qubits, all the cloud data available in the world can be composed together in a single quantum computing system. But I have to tell you that right now, this quantum computing era is not fully fault tolerant era. It's a noisy intermediate scale quantum computing era. For this reason, we need more number of qubits to accommodate the all data in the world. So we are using two things. I have already told you about the first thing, that we can put 0 and 1 together. This is called qubit superposition or quantum superposition. So we have 0 and 1 together. Whenever we are measuring it, depending on probabilistic value, it will give either 0 or 1. Say in a qubit, I am putting 25% 0 and 75% 1. It is not that easy, but I'm putting it. Now, if I measure it 100 times, then you can see that near about 25 times I will get 0, as I am putting 25% 0. And I will get near about 75 times 1, as I am putting 75% 1 within a single qubit. The next thing, we are relying on quantum computing. Next phenomena, we are relying on quantum computing, that is quantum qubit entanglement or quantum entanglement. Now, what is this quantum entanglement? Quantum entanglement means we are basically entangled more than one qubit together. Why? The question is why. To have one qubit's value, that means to measure one qubit's value, if the qubit is entangled with another qubit, then by measuring one qubit value, we can actually predict what is the value of other qubit. Now you can ask why it is required. It is required because whenever you are measuring qubit, you are not able to measure the qubit again to get the same value. Why? Say we have some value within the qubit. When I am measuring it, I'll get the value, and this qubit collapsed. So we'll not get the value again whenever we are measuring. The quantum state is not available over there after one measurement. So we need quantum entanglement so that we can measure one qubit and we can get the value of another qubit. It can be used in different quantum paradigms, like it is hugely used in quantum cryptography, quantum teleportation. A lot of things are there where we are using this quantum entanglement feature directly. Now, I'm talking about the leap. Why we have quantum leap? See, we have a lot of problems over there in the world, which is basically considered as a hard problem right now. Still, we have our high performance supercomputers available with us with gigahertz capacity. In the previous slide, I have told you that if we have a classical computer with a gigahertz capacity, classical supercomputer with a gigahertz capacity, then for a 2048-bit keys, it will take 317 trillion years to decode. But if we use quantum computer, fault-tolerant quantum computer, still which is not available, but we are actually approaching to that era, quantum era, fully quantum era, fault-tolerant quantum era. Then it will take only 10 seconds for say 4,000 qubits quantum computing system. This has already been theoretically proved, but not practically. For this reason, right now we are using the same RSA and Diffie-Hellman protocol for the public. So here I want to tell why this quantum leap has been taken to solve hard problems, to build bigger quantum system to solve hard problems, minimizing the errors we have. I have already told, because our quantum computing devices right now are in a noisy intermediate scale quantum era. So stopping or minimizing the amount of error by increasing quantum volume. Quantum volume is a term, technical term, by which you can measure how much error you have. So if the quantum volume is bigger, then error rate will be minimized. By increasing quantum volume, minimizing the errors, building more number of qubits together, with more number of qubits together for building a quantum system. And obviously, after doing it, to use some efficient algorithm to solve the hard problem. For this reason, this quantum leap is right now over there in the world, all over the world. This is taken from IBM source because you know that, all of you know that IBM is basically pioneering this particular field. Still, IBM is not providing the first quantum computer, is not the provider of first quantum computer. Rather, D-Wave system is the first provider of quantum computing system. But with a volume of superconducting qubit devices, IBM is right now leading this particular way of quantum technologies and quantum computation as well. We are actually, I have pointed out over 3 horizons: Horizon 1, Horizon 2, and Horizon 3. Horizon 1 is already there. We are actually doing different chemical design, chemical simulation, drug discovery, protein folding problems, devising protein folding problems, designing protein folding problems in quantum system, quantum scenario. Then we have in automotive industry, we are doing material discovery, molecular biologics in biotechnical system. So we are doing it. This is Horizon 1. The range of Horizon 1 is from 2018, that is from past, to 2025. But if you are thinking about Horizon 2 and Horizon 3, it will take next decades or 15 years of time to reach where we can do the predictions on weather forecast, the predictions on traffic congestions in different heavily trafficked road, heavily trafficked area. Then we can do financial predictions in finance sector. So these are the three horizons. We are right now in Horizon 1, Horizon 2, and Horizon 3 is going to come with their efficiency and all, with quantum data, in near-term quantum data. Now, if we consider the major involvement, a lot of universities, lot of companies who are involved in quantum, if we consider the major involvements among the tech giants, then there are 2 architectures we have. First, two promising architecture we have. The first one is built with superconducting qubits, with superconducting technology. And the second one is basically using annealing technique. They are also using superconducting technology, but their policy, their technique is quantum annealing. We have over here different tech giants who are investing a lot of money over here in superconducting architecture like IBM, Rigetti, IonQ. IonQ is basically right now collaborated with Honeywell and Microsoft. Then we have Xanadu, who are basically working on quantum software itself. And the next thing is quantum annealing, which is a physical technique used by D-Wave system. D-Wave is the first company who has commercialized quantum computers in 2006. And the market map, the whole market map of quantum devices and quantum technology would look like this. For quantum encryption, you have Indian company like QNU Lab, you have IDQ, which is basically a company from Switzerland. Then in hardware, you have Rigetti, US-based company, Canadian as well, DOF, INQ. In software, you have one Qubit. In the promising names are one Qubit. In quantum AI and quantum machine learning, you have Xanadu. Then in but for the quantum cloud system, you have INQ, Rigetti, IBM as well. For quantum circuits, they are working on a silicon quantum. So all the European company, US-based company, some company from China and India, mainly are working on different quantum devices, different quantum technology, different quantum software, quantum machine learning, quantum AI, and obviously in quantum cryptography or quantum encryption. So these are the market map right now in this current scenario. Next, I'm coming to the actual part. That means where quantum can do something. First and most promising area is quantum machine learning, because we have a lot of hard problems over there in quantum machine learning. We have hard problems for prediction. We have hard problems for regression. We have hard problems for training. We have hard problems for finding the principal component analysis. We have hard problems for removing the feature. That means feature elimination. So we have a lot of hard problems in quantum machine learning or quantum AI. Right now, in this quantum era, we don't have a fully quantumized version of algorithms which can solve a quantum machine learning problem or quantum AI problem. Rather, in machine learning era and optimization era, that is another part of quantum technology. In these two era, we are basically using a hybrid approach. That means we have classical machines, we have quantum machines, we have the feedback system. The input has been given to the classical machine. Classical machine is preparing the quantum input for the quantum module. It is given to the quantum module. Quantum module is basically doing the calculations very faster. Then it will basically giving a feedback to the classical module as output. After measuring the feedback, the classical module is changing its parameter and again give that particular thing to the quantum module to find out the best optimized output. So the thing is not that easy, but the overall thing is look like this. You are giving input to the classical system. The classical system is basically making the data in quantum data. Then quantum data has been given to the quantum devices, quantum module. Quantum module is calculating, giving a feedback to the classical module. Classical module is basically checking whether how much near to the required output it is. Then it is changing its parameter and again give it to the quantum module. And the process going on till the classical module satisfied with the value that yes, it is our required value, actual required value. So it is a iterative model, hybrid iterative model. And with this particular model, we can solve a lot of problems. Right now, in this era, we have different types of algorithm like QAOA algorithm, quantum approximate optimization algorithm, or we have QUBO algorithm, quantum quadratic unconstrained binary optimization algorithm, which can be solved by quantum. So we have this type of algorithms over there for handling quantum machine learning and quantum AI. Except this, we have quantum variational eigensolvers. Right now we have different modules for principal component analysis, to do the regression, to do the correlation among the given huge set of data. All these things can be used in first financial pricing prediction. That means what should be the predictive value of a finance product, which is basically a tough job right now using classical devices. Then resource utilization predictions. Resource means in different industry, you can use that particular resource utilization prediction. Like energy sector, you can have a lot of resource. Like for renewable energy, you can have a lot of resource. You can have a lot of type of renewable energy over there. So you can, depending on the situation, depending on the given input, you can actually predict which particular resource should be right now good for generating energy in energy sector. The same thing, resource utilization prediction can be used for your logistics. That means in the logistic industry, there are a lot of resource is used. The vehicle use has been used, manpower has been used. The different machinery has been used to pack and move the goods from source to destination. So based on that, resource utilization you can do in logistic industry, where quantum can do it in a real time. You need not to wait for the allocation, resource allocation. Then obviously weather forecasting is having a lot of data from the previous weather scenario, weather conditions. The prediction or forecasting of a particular weather, a particular time frame can be done, and it can be done in real time as well. Since these all, then we have grid optimization in renewable energy, and automated trading is also a financial instrument to do stock trading or cryptocurrency trading in with an automated system for buying and selling automatic. So yes, with these machine learning or AI approach, we can invade. There should be an invasion over there, because it will take a lot of time. Either it will be in real time or it will take huge amount of time. Say in case of weather forecasting, we are doing weather forecasting with our satellites, with our different offices situated over there with different machineries in different part of our country. We can forecast weather, but weather forecast should be real time. We don't know when a landslide will come. We don't know when water burst will come, rain burst will come. So it should be real time. So either if it is not real time, it should be real time, or it will take a huge amount of time to predict or determine a particular value over there. Then we have quantum cryptography. This is the first situation. Initially, whenever we have quantum, we have right now we have they are all vulnerable, right? RSA, ECC, AES all are vulnerable. ACC is basically getting less quantum key. For this reason, we have a technology called quantum key distribution. QKD stands for quantum key distributions. Here we are using a quantum channel over there, and we are actually sending the data from public channel, but key has been sent to quantum channel. Then this cryptography can be used in defense, in cybersecurity, in financial transaction, in blockchain technology, because all of them are highly secured transaction to do. Next, we have post-quantum cryptography. Except this quantum technique, we have different techniques. We can, like hash-based cryptography, code-based cryptography, lattice-based cryptography, multivariate cryptography. We have different quantum techniques over there for post-quantum cryptography. Except quantum, we can also use it. Next, we have the next part. The first part was quantum machine learning and AI. Next part was quantum simulation. Simulation means you are simulating a real-life devices, a real-life natural element using quantum system. So physical molecule can be simulated in a quantum molecule. By this policy, we can do it right now. By this policy, we can discover a new drug. We can do protein folding for discovering new antibiotics. We can use it at automotive industry to measure the performance of battery, to create a new material for battery, which can be much more stable with its charging and leakage. Then we have another material discovery for different industries where materials are actually required. Then the next part, the third thing we can do in quantum optimization. Here also, I have already told, it's an iterative process. So we have quantum module, we have classical module. It is basically iterating with one another's output, and then there is a stopping criteria by which we can get the optimized value over. We can use this quantum optimization for our financial portfolio optimization, risk analysis, fraud detection in finance domain, vehicle route optimization. That means we can optimize the route, and obviously it can be used in supply chain planning. This is the last part I wanted to say, that in future, right now, it is taken from IBM. The source is IBM. In 2021, we have 128 qubits, near about 128 qubits with 64 quantum volume. Quantum volume is basically used for noisy quantum device. Here you can see that within 226, we can have millions of qubits to solve a particular hard problem. So if you have any query after that, it's a very small description on quantum. If you have any query after that, you can contact me at my mail. It's Mrityunjay, Mrityunjay, at QRD Lab, Quantum Research and Development Lab.com. Thank you. Thank you very much.